Hey everyone, welcome back for another lesson in chemistry. This time we're taking a look at stoichiometry with multi-unit conversions. So far in stoichiometry, we have learned that we can convert moles of a substance A into moles of a substance B by using the mole ratio, essentially multiplying by the coefficient of B over the coefficient of A from a balanced chemical equation. In addition to this, we've seen that we can take the mass of a substance A, convert it into moles, then apply our mole ratio into moles of B, and take those moles of our substance B and convert it again into a mass. Essentially, stoichiometry is just a way of relating two quantities together from a chemical reaction. It all comes down to getting moles. So once we have moles of one substance, the balanced chemical equation will help us get to moles of another substance. All that matters is how we get to moles, and essentially that is our goal. So let's look at an example of where we're trying to find another chemical quantity, but this time we're not just limited to mass. So let's calculate the volume of hydrogen gas at STP that would be produced from 100 grams of solid aluminum. So in this case, we're asked about volume and given a mass. Now at this point, we've done mass to mass. We haven't really discussed volume yet. But since everything for stoichiometry essentially comes down to getting your moles, we just have to first find a way to get our moles. Since we have 100 grams of solid aluminum, we're essentially starting with the mass of A, in this case is aluminum. Our target here, though, is the volume of hydrogen. So currently, with our stoichiometry map, we're not including volume, but we know that moles and volumes do share a relationship at STP. So we can actually take our moles of B and find volume by knowing that at STP, 22.4 liters is equal to 1 mole of any gas. So here we have our avenue for finding volume. Essentially, we're going to take the mass of our substance A and convert it not to mass of substance B this time, but this time's volume. In essence, stoichiometry is just either finding your moles or using your moles, but everything comes down to the mole. Our first step is always figuring out how do we get our moles, and then our final step is always figuring out how to use the moles. So in the case of this problem, we have 100 grams of solid aluminum. So we're going to start with 100 grams of aluminum, and we want to change this into moles. So we are going to divide by the molar mass of aluminum. In this step, we are essentially converting from 100 grams of aluminum into moles, or rather going from mass of A to moles of A. Our next step now is to do the mole ratio. We're not interested in aluminum, we are interested in the volume of hydrogen. So we will need to take our moles of aluminum after this step and convert it into a volume of hydrogen gas. And so to do that, we need to convert this into moles of hydrogen, and so we must chain on the mole ratio from the balanced chemical equation. Now, if you see above, our equation is not yet balanced. So before we can proceed, we have to make sure that we are working with a balanced equation. And so a balanced equation will have a 2, 6, 2, 3. So now that we have our complete balanced equation, we can get our mole ratio. The numerator of our mole ratio is always what we are interested in finding or converting into, in this case, hydrogen. The denominator is going to be the substance that we're beginning with, in this case, aluminum. So if we look at our mole ratio from hydrogen to aluminum, we are looking at a 3:2 ratio. So we're going to take our 100 grams of aluminum, divide by its molar mass. Doing that will get us the moles of aluminum. Then, in our next step, we'll be converting this into moles of hydrogen. Finally, after we do the mole ratio, we'll have moles of hydrogen, and now we just have to convert that into a volume using the fact that at STP, 22.4 liters of any gas is found in 1 mole. So our third step here will get us the liters of the hydrogen. So we work this all out, taking our 100 grams, dividing by the molar mass of aluminum, multiplying by the 3:2 ratio, and finally multiplying by the 22.4 liters per mole. We get that 100 grams of solid aluminum will produce 124.5 liters of hydrogen gas. So our mole map is essentially extending stoichiometry beyond a mass-to-mass conversion. So long as we have a unit that can work to and convert with moles either to and from, we can do stoichiometry with it. This also applies not just finishing with volume, but if I was to begin with the volume as well. So volume all ties into moles, and it just matters, are we beginning with it or are we finishing with it? The other mole conversion that we've seen in the past also involves particles. So if we have particles of a substance A or are looking for particles of a substance B, we would just use Avogadro's number. These three mole conversions just provide us avenues for finding moles in order to do our stoichiometry. So let's see an example of what that looks like. How many molecules of water can be produced in the reaction of 12 liters of hydrogen gas reacting with oxygen at STP? So in order to perform any kind of stoichiometric conversion, we will need to find our chemical equation. So in this reaction, we're told that hydrogen gas reacts with oxygen gas and is producing water. We must balance our equation, and now we're ready to begin. So here we are looking for molecules, aka particles of water, and we are given a volume of hydrogen gas. So we are no longer even dealing with mass. Essentially, we're dealing a volume to particle conversion. But for any kind of stoichiometry, our first instinct has got to be get your moles. So we need to figure out how can we go from 12 liters into moles. Well, we know that volume and moles are related at STP. So we're going to take our 12 liters of hydrogen and we're going to convert this into moles by dividing with 22.4 liters per mole. This step right here will get us moles of hydrogen gas involved in the reaction. Once we have moles of hydrogen, we're going to go ahead and apply our mole ratio. So for our mole ratio, we're looking for water, and so it is a 2:2 ratio of hydrogen to water. Once we perform this step, this will get us moles of water. Finally, we're looking to get the particles of water, and so we take our moles of water and multiply with Avogadro's number. And that is 6.02 times 10 to the 23 molecules for every 1 mole. Once we work this out, we end up getting that there are 3.23 times 10 to the 23 molecules of water present. So this final step converted our moles of water into particles of water. So we can see here that stoichiometry really isn't limited to any one particular unit. So long as we are able to find moles and use our moles, we can figure out how to relate to different chemical quantities. A fourth method of introducing moles is with molarity. Now, molarity refers to the concentration of a solution. And what concentration is, it's just a measured amount of solute within a specific amount of solvent or solution. Essentially, concentration just tells you how much solute, something that you're dissolving, is present in a mixture of that with another substance. A solution is just a homogeneous mixture of two substances that share the same state of matter when mixed together. So the concentration essentially just gives you an idea of how much the lesser quantity is present in the entire mixture. Now, molarity is found by taking the moles of solute, whatever you're dissolving, dividing it by the total liters of solution. So here we have another way to relate moles together, but this time with solutions. Let's take a look first at how to work with molarity. So we want to determine what is the molarity of a sodium chloride solution that contains 5 grams of sodium chloride dissolved in 35 milliliters of water. So we are looking for molarity, and we know that it's going to be moles of solute. Our solute will be sodium chloride divided by the liters of solution. So our first step is to take our 5 grams of sodium chloride, convert that into moles. So we will divide by the molar mass of sodium chloride, and we get that this is 0.086 moles of sodium chloride. So we have 0.086 moles of sodium chloride. 35 milliliters of water is 0.035 liters. And we get that the solution would have a concentration of 2.4 molar. Okay, now let's see that in action with the stoichiometry problem. We're told here solid sodium metal is added to 150 milliliters of water at 0.5 molar solution of copper 2 sulfate. The balanced chemical equation is given to us below. Let's calculate the mass of copper that can be formed from this reaction. So we're looking for the mass of copper, and the only thing we know is the measurement of the solution we're given. This changes nothing. Whenever we're approaching a stoichiometry problem, our first thought has always got to be, get your moles. So we have to use the information given to us to figure out how can we use this to get moles. Now in this question, we're given a molarity and a volume. And like we just saw, molarity equals to moles over liters. So if we have molarity, we have volume, we can find moles of copper sulfate. That's exactly what we're going to do first. We're going to take our molarity equation, and we're going to rearrange and see that moles is just molarity times volume. So the moles of copper sulfate will equal to 0.50 molar times 0.150 liters, and we get 0.075 moles of copper 2 sulfate. Now that we have moles of copper 2 sulfate, we can go ahead and apply our mole ratio. So we're going to take our 0.075 moles of copper 2 sulfate. We will convert this into copper. It is a 1-to-1 ratio from the balanced chemical equation. So that will give us 0.075 moles of copper. And now all that's left is to take our moles of copper and multiply by the molar mass of copper. Doing so gets us 4.8 grams of copper that can be produced when sodium metal is added to 150 milliliters of 0.5 molar solution. So it really doesn't matter what exactly we're beginning with or what we're asked to finish, so long as we can convert into moles and convert out of moles, we can approach any stoichiometry problem. So just to add to our stoichiometry web, we've seen that we can convert with volume, mass, and particles. And now the last step is being able to add in molarity. And that is with the fact that molarity equals to moles over liters. The same thing can apply where if we're looking for the concentration of a solution, we can always just take the moles we're given and just divide it by the volume of whatever solution we're given. Our stoichiometry web here essentially details out and explicitly states all the different ways that we can convert with moles to do stoichiometry and exactly what we need to look for and what to use.